All right, so these notes are going to turn the heating curve on its head, kind of flip it around and take it in the other direction. So we're going to start with, if this were water, steam, which would be at a very high temperature, and it would decrease in temperature as it loses heat constantly until it gets to the condensation point, which is the boiling point for water. And then it will flatten out. That doesn't mean it's not still losing heat. It is still losing heat, but at this point it is changing phase, and that is at a temperature of 100 degrees Celsius. And that'll continue until all of it has changed phase, and then it will begin decreasing in temperature again until it reaches the freezing point, which would be at 0 degrees Celsius, assuming below this was less than 0 Celsius. And that would be the freezing point of water. And it will plateau there until all of the water is frozen solid. And then it will continue to lose heat, and this time it will actually decrease in temperature like so. So let's do some math problems that involve a cooling curve. This will involve table B from the front of your reference tables and the equations from the back of your reference tables having to deal with heat. So I'm going to bring those in. So here they are, table B with our constants and then the heat section of your equations. I just want to remind you, when we do use a cooling or a heating curve, which equations you use when. Whenever you have temperature changing or a slope to the line, you're going to be using the equation from the heat section, Q is equal to mc delta T. Delta T being a change in temperature, so it makes sense that you would be using that equation. The top plateau, the higher plateau, that's the condensation point, since this is a cooling curve. But if you were going in the other direction, that would be the boiling point. It involves a vapor or a gas, so that would involve the heat of vaporization. So the equation we're going to use for that top plateau is Q is equal to mHV. And then that lower plateau, which is where freezing is going to be occurring, is where we're going to use Q is equal to mHF. I think of that F as being freezing. So Q is equal to mHF. All right, so that'll hopefully help us pick the right equation in each of these questions. First question, how much heat will be lost? Okay, we're losing heat. That implies a cooling curve. When 50 grams, so that's going to be our mass of steam condenses. Okay, so we're condensing. Condensing happens at this upper curve or this upper plateau that we are talking about with the cooling curve. So the equation we're going to be using is Q is equal to mHV. Q is what we're looking for. That's our question mark. And then M was given in the question, so we'll just plug that in. And HV is actually a constant. Here it just says heat of vaporization, but when you look on table B on the front of your reference tables, it's 2,260 joules per gram. Our grams cancel out, leaving our units to be joules. So when you multiply those, you're going to get 113,000, that's a comma, joules. Don't forget your units. We're not going to have any naked numbers. That would be shocking. All right, next question. How many grams of water, so in this question we're actually going to be looking for M, will freeze, so we're talking about that lower plateau, when 2,500 joules of heat is removed. So this is our Q. So up here we said that when we are talking about that lower plateau, we're going to use this equation. Q is equal to MHF. This time we have Q. I'm going to move over here so I have a little more room. We're looking for M, and HF is a constant we find on the front of our reference tables, 334 joules per gram. To get the M alone, we'll just divide each side by 334 joules per gram. These cancel, why didn't I use red? These cancel out. Joules cancel out, leaving 1 over gram, which is just grams. So now we just have to do the math. That's 2,500 divided by 334, which when we round that, and I'm going to round it to 3 numbers, is 7.49, and our units we said were grams. Okay, so let's try another example. This time we're going to have one where temperature is changing. This is tricky because heat's lost in this one, so we're gonna need to deal with that at the end of the problem. So the question's asking how much heat is lost, so we're going to be looking for Q. They gave us 125 grams of water, so that's M. And that it changed temperature from 95 to 45. Previously, when we talked about delta T, we said delta T is T final minus T initial. So that means, in this case, 45 minus 95. And when you do that, you're going to get a negative number. And that may seem weird and it may be uncomfortable, but that's actually what we need because we're going to be losing heat, which means that Q is going to be negative. So that indicates a loss of heat. There's a couple ways we can go about this. I'm going to complete this problem using the negative, and then I'll tell you another way you could do it if it works better for you that way. So since we're talking about temperature changing, that means we're going to be using Q is equal to MC delta T. Q is what we're looking for. M was given as 125 grams. C, expressed here in words, you can find as a number here. So that is 4.18 joules per gram Kelvin. And delta T, we just figured out, is negative 50 degrees. When we're talking about a difference in temperature, a degree in Celsius and Kelvin is the same, they cancel. And grams cancel, so our answer is going to be in joules. So all we're going to need to do is multiply those 3 numbers, taking into account that one of them is actually negative. So 125 times 4.18 times negative 50. And we get negative 26,125 joules. That's one way you can do this problem, where you're actually using the negative from your delta T. The other way you can do it, which sometimes works good for students, is you see that heat is going to be lost in the problem. It tells you that. You don't necessarily have to use this negative in the problem and get a negative at the end. What you could do alternatively is do all of this problem without the negative for the delta T, and when you write your answer, you're just going to write 26,125 joules lost. So you could write it this way, not using that negative for the delta T, or you could write it this way. Either answer is acceptable. You can't have the negative and have lost, though. And that's how you would do problems using a cooling curve. Not very different from a heating curve.